Okay, well, I don't know what's happening. Other than I'm a couple minutes later than usual, but like Zoom is many times slower than it used to be booting up. I don't know what is this the new world of AI? I'm not sure. But anyway, today, the last week of classes. So we're here on the 30th, and we're going to continue talking about the standard template library. I just closed the server for tutorial 5. You have tutorial 6. And assignment 4 to finish. Just keep an eye out. I might have to update assignment 4, the specification. It's hard to get everything right, especially, it's just because you make small little changes and then you make them in one place and forget to make them in another. And now you have a spec and a test that doesn't match. But I don't think I think all of that is solved. But I think I expect you to put all the player classes in basically one set of files, right? A header and a source. And I don't think I put that on the specification. So there may be problems with the compilation process if you don't do that because the server uses its own makefile. Anyway, I'll clear that up this afternoon. So yeah, that's where we stand. This week, I should be able to release the practice final, working on assignment 4 is as good of preparation as the practice final, right? It's all basically, again, the practice finals assignment 4, but like hacked up a little bit and simplified a little bit. But yeah, questions? Okay. Can't figure out how to turn that spotlight off. It is really bright. All right, so today we are going to continue to talk about the standard template library. Now, this stuff does not appear on your assignments, but it does appear on your last tutorial and a little bit on the exam, right? So some of the multiple choice questions you might see stuff on, say, basic use of iterators. So on that topic, well, last class we had seen that we could use iterators to access list elements, which it wasn't exactly clear how to access list elements without them, right? Because vector, you can use the subscript operator, but list did not have any subscript operator. So that brings us to categories of iterators. So there are, although they all share the similar syntax, there are versions that have more things that you can do with them. So at the top is the sort of weakest. So input, output, and forward iterators. And to be honest, I don't really know the difference. I looked for differences and I cannot find them. So those will basically be in one category. Because on a stream, basically, you can only walk forward anyway. Generally speaking, if I'm reading some bytes in from somewhere, then I get one look at them and I gotta, process them as I go, and I can't really go back because, well, whatever. Once they're processed, they'll probably disappear. And then there's bidirectional, which is, well, that's like our doubly linked list. We could walk forward, and we can use reverse iterators to walk backwards, or we could even walk backwards with a forward iterator. And then there's random access, which is, basically your vector class, where I get direct access using the subscript operator, and also I can do pointer arithmetic. So every category contains all the abilities of those above them, and they're all syntactically the same, right? Dereference and increment and all those things work the same. All right, so the different container implementations come with their own category of iterator, right? So list is bidirectional, but does not have random access, which sort of supports what we know about linked lists. Vectors have it all, right? They support random access, and then basically they go forward, backwards, they can jump around, they can do all of those things. So all iterators support these operators, right? So I can dereference. I guess also I should put in the arrow operator. I can increment. I can assign, right? One iterator to another. I can check to see if iterators are equal or not equal, right? So I get increment, I don't necessarily get decrement. Forward, bidirectional, and random access support. Well, now I have a function that I can call on my collection class that returns an iterator that points to the first member or returns an iterator that points to just past the last member. And of course, I also get the increment operator here. If I get bidirectional, then I get the decrement operator as well as reverse iterators. And then random access, I get subscript. Well, now I can compare iterators, so it kind of makes sense to, whereas it doesn't necessarily make sense with the list, right? Because a list is not really, I guess, I mean, it is in sequence, but it doesn't really keep track of the sequence. So if I have, an iterator that points to the fifth member and an iterator that points to the second member, there's no way to compare those two in terms of where they occur in the list. But for vectors, of course, everything's indexed, so I can compare. I can do pointer arithmetic, and yeah. A couple of performance tips, right? Prefer to use the prefix increment in decrement rather than postfix, unless you on purpose want to use postfix for a specific reason. Right, so the for loops, I've been showing you stuff like this. For it equals something dot begin, it not equal to, what am I doing? Not equal to something dot end. Well, rather than calling this function over and over again in this for loop, I could just store that iterator, right? Just make an iterator that says points to the end, and then that's going to be a little more effective. Possibly your compiler would optimize that, but all right. All right, so that's iterators. So containers are classes that contain a collection of objects. Basically everything in a container, all elements have the same data type, right? To within inheritance, of course. We get three basic types: sequence, associative, and container adapters. All these containers provide the basics, right? So I can make one, I can copy one, I can destroy one, I can assign one to another. There are insertion and delete member functions. These take iterators as arguments. They're a little bit awkward, as we'll see, or we did see. We have some size-related and relational operations, right? So we can compare, for instance, two linked lists or vectors or whatever. And then what they will use is lexical graphical order. And you can think of that as, well, if I have, let's say, two linked lists, and I wanted to compare them, well, what should I do? So this is pointing to null. So what does it mean for one to be greater than the other? Well, you could look at size, but that's not really telling you much. Actually, let's make them the same size, just to be sure. Well, what we're going to do is we're going to compare the individual elements, and you can sort of think of it as, instead of linked lists, you can think of these as words, strings. And so how do we compare strings? Is we compare the elements as we walk through. So, right, if I have, for instance, A, C, D, and A, C, E, then how I compare them is I look at the first two elements and they are equal. So I move to the next two and they are equal. And then I look at these and it turns out that D is less than E. All right, so that means the first list comes before or is less than the second list. And although we did it with characters, that sort of generalizes to any data type. Yes. All right, let's get into the example. But before we get to the example, if you're using your classes in containers, a few good ideas, right? So you should maybe implement a copy constructor. In particular, if you have a complicated class, right, and you have, if you need to make a deep copy in particular, then it's very important that your copy constructor and assignment operator work correctly. But also for some of the algorithms that we're going to use, then you might want to overload these operators. This is not strictly necessary because you can always just pass in another function. But by default, that's what these algorithms will use, the operators. Okay, so let's look at streams as containers. That is, we're going to apply an iterator to a stream. Which stream is the input and the output streams, and in particular, cout and cin. We're going to wrap them in iterators and see what kind of things we can do with them. Okay, so I am going to try to remember the syntax for this because my autocomplete's not really working. Is that it? I might have to look it up. Yeah, let's look it up. Well, that's it. I just don't need the, that's it, right there. So let's put output stream, and then we're going to pass in our standard output. Okay, so we've now wrapped our cout in this ostream operator, and that means we can do some funky stuff like this. Right, and then, well, it's an iterator, so let's increment it, and then do something like this. But I'm not actually doing this properly. OS is an iterator, and I cannot assign a string to an iterator. I can only assign an iterator to an iterator, but it does behave like a pointer. So I can dereference it. That returns the string, and then that can assign the that particular string to our iterator, which will put it on the output stream. And am I in the wrong place? Yes. Awesome. All right, I'll just switch. Let's just copy this. Okay, there we go. Hello world again. Okay. Well, I did manage to print to the standard output, which is the console, using this sort of weird syntax now. Of course, I cannot, since this only takes strings, right? I cannot actually send an end line to it, right? So you might think that we could do something like this. And no, it does not like that whatsoever. So if I want a new line here, I have to do it the old-fashioned way. I have to put it, I have to put the new line character in. Okay, hello world, hello again. And so we took that nice, or what I think is nice, a lot of people hate it, But that nice stream sort of where I can just chain all of these streams together, and now we have this ugly code. Yeah. Yeah.
How would we like okay, except for like strings, like how else would we do that? We have no plans.
Or why would we want to do this, I guess. Yeah. I'll kind of show you because you can take like, so here I'm assigning it just string literals, but I can take a vector, let's say, of strings, and I can copy it to the output stream. And then it'll write my whole vector all at once. So yeah, that might be anything else. I'm with you. I don't know. Maybe maybe it's useful also in files. Because instead of string here, I can use like student or whatever it is I'm storing. And then I can write to files really quickly. But, and you're going to see basically all of the things that we do with algorithms, or at least the algorithms we use, they're quite simple to write yourself, right? For the most part. But we're going to take it anyway. It's good to know if you're ever in C++ and you see somebody else doing this, that you kind of know what they're doing. But yeah. Other questions or comments? Okay. Well, here's another one. I can just take this away, actually, as far as the output stream goes. I mean, once I send hello world there, there's no going back, right? So here I print hello world to the console, and then, I mean, whether I advance it or not, the next string is going to, you know, I mean, I can't overwrite this. I suppose I could, if you really wanted to dig deep into how a console works, but generally speaking, the canonical use of it does not support that. So yeah, I don't really have to increment this one. But let's now try an input stream iterator. So I'm going to do the same thing, change it to input stream, grab C in, and wrap it in this iterator. And then I'm going to say, I'm going to do a couple things here. Oh yeah, this. The other thing is that I believe I don't even need to dereference these. So C++ is particularly frustrating in that I find it frustrating at least that it allows sort of the willy-nilly syntax. I mean, I don't know. I'm kind of more comfortable when syntax is, there's one correct way to do it, and then and that correct way sort of suggests the underlying process, right? Like I'm dereferencing here, that suggests something important. Of course, the people who made the language don't agree, so I don't know. They've probably thought about it a lot more than I have. All right, so the input stream. Well, one thing that you may have noticed when I ran this is that it paused there and waited for me to input. So as soon as I wrap this in an iterator, it starts waiting for my input, right? So for instance, if I do, please enter a string, and then I can do, well, I need a string that I can read into, and then so temp equals, and in this case, I'm pretty sure you do have to dereference. And then I could put, okay, well, it compiled, that's a good sign. Hello, hello again. And now I said, please enter, but it doesn't write, please enter. It just sits there, waits. So I'm gonna say, hi there. And please enter a string. It says you wrote hi. So again, like CIN, right? It reads one token at a time. The white space acts as a separator. So even though I wrote two words, it just grabbed the first one. And if I want to grab both of them, or if I expect there to be two words, then I can say, temp1 equals this. Okay. So now I'm reading in two strings, and I'm going to presumably print them both. I should move that up. But anyway, so hi there. And it says, please enter a string you wrote hi and hi. So first thing, let's move this up here where it can be sort of useful to us. But it read hi twice instead of reading hi and there. So in terms of output streams, I do not need to advance the iterator, but for input streams, I do, right? Because it is actually sitting on a buffer somewhere. It's not, once I send this to the console, I can't take it back, right? I cannot reverse. But for the input stream, it's just sitting there. I read the token, I copied it, but I didn't advance it. So let's advance. And then that should grab both words. So please enter a string or two strings. And then says you wrote two end strings. Okay, so for output streams, I don't need to advance. For input streams, I do. I'm pretty sure you cannot do this, but let's try it just for fun. Once I've advanced it, it of course empties that place off. Yeah, it doesn't even have an operand or an operator for that. So yeah. So these are both examples of stream iterators. They only move in one direction. This one moves implicitly. I don't have to advance it, but this one I do have to advance it, and I cannot go backwards, right? Once I take something off the buffer, I can't get it back. I could store it and then look at it later, but all right, questions? I mean, the big question is why would you ever do something like this? And yeah, I don't know. So here is the, yeah, so technically we should, I mean, I like it better when you dereference, even though you don't have to, because it does remind the reader that, hey, this is an iterator, not a string. So that can be confusing. Oh yeah, let's do example 4 as well. So we're going to see some of this in action. I'm going to make a vector of strings, and then I'm going to have a temporary string just to grab whatever the person enters. So it's enter word starting with end. I'm going to wrap my CIN in an iterator, and then I'm going to start reading from that. Right? And while this string is not equal to end, I'm going to push that string onto the vector. I'm going to advance my iterator, and I'm going to read the next one. And then down here, we're going to print them. And how we're going to print them is using, well, we're going to OStream iterator. I guess let's out iter. We're going to wrap it up there, and then I'm just going to copy. I'm going to use, so you can see up here, I've included the algorithms library, and I'm going to use a copy algorithm. So I'm going to copy. So I want to copy from the vector to the output stream iterator. So vector is called, what is it called? Words dot begin up to words dot end. So I want to copy the entire vector, and I'm going to copy it to this output iterator. Right, so I want to copy everything from words.begin to words.end, starting with this iterator and just advancing the way you normally would. Now we're using an output stream here, but of course I can put any iterator from any type of container. So yeah. Enter words starting with end. Hi there. How are you? I and am well. And then, all right, well, there's not a lot of formatting there, but it goes up to the I and then it stops. And then we copied it to the output stream. Okay, well, that's kind of ugly. So we could, well, there's a way to sort of format this output iterator and tell it that every time you write something or assign a string to this, then you will also assign one of these strings, right? So as a separator, essentially. And now it says, hi there, how are, and then it ends where it's supposed to. Right, and well, I don't have to use just a space. I can, if I wanted to, I can use different types of separators, right? It takes any string at all. So hi there, how and are you? And it says hi there, and now this this star is the separator. It's also, right, here it doesn't separate anything. It's written after the string. But so yeah, every time I write one thing of whatever, I write one of these. Yeah. So questions? Okay. I believe that's it for that. All right, so we're going to see this copy also works with arbitrary containers, but it works with you know, streams as containers. So let's take a closer look at some sequence containers and how we would use iterators and algorithms with those. So we're going to look at vector, list, and dec. Probably just vector and list though, because we are a little bit short on time. Yeah, we should be familiar with the underlying implementation of vector, right? It's an array-backed data structure that grows as needed. Incidentally, I'm pretty sure it never shrinks, right? You can shrink it yourself manually, but generally speaking, it'll grow, and then if you start deleting a bunch of stuff, it just stays huge. Which is, it does make sense statistically to do that. If ever your vector reaches 1 million elements and then goes back down, then probably at some point in the future, it's going to go back to 1 million, or close to it. All right. Let's look at 5. So we're going to do these things specifically on the vector now. So yeah, I'm going to read in a bunch of strings, the same as before, push them onto my vector. I'm going to copy them to the output. Oh yeah, we're going to take a look at a couple things. One is capacity. So yeah, capacity is essentially the size of the backing array. Let's run this. Hi there. How are, now that's 4 words. So at this point, the backing array has size 4. I'm going to put 5, right? So I'm going to put a 5th word, and then I'm going to put end. And hi there, how are you? And now the capacity of words 1 is 8, right? So again, the backing array doubles every time. So it went from 0 to 1, first of all, and then it went from 1 to 2, and then 2 to 4. And then when I added that 5th one, it doubled to 8. And that's where we get this capacity from. All right, so as we grow, this capacity will change, and it should double every time. Okay, well, there's exceptions to that. So what I'm going to do here is I'm going to declare a second vector of string called words2. I'm going to give it an initial size. We'll see why in a moment. And then I'm going to copy all the words from words1 into words2 starting at words2.begin. Okay, this is the same copy command that I use for the output stream. And then I'm going to write both of these strings to the screen. No, sorry. Why do I have this line twice? I'm not sure. I'm going to write words2 to the screen, and then we're going to write the capacity of words2. Okay, so I'm going to do the same thing. I'm going to put 5 words on it. So hi there, how are you? That is 5, and then end. And then it prints out hi there, how are you? And the capacity of words1 is 8. I copied words1 into words2. It says hi there, how are you? And the capacity of words2 is 5. So here I explicitly set the capacity to the size of words1. All right, so that's one thing you can do with your vectors. If you know beforehand that you need to store 5 elements, then you can set the size, and then you don't have to go through that growth routine. Of course, you're setting the size explicitly here, right? So if I looked at words2.size, it's going to say 5 as well, even when it's sort of, in some sense, empty. So yeah, and if I didn't do this, let's say, okay, so I just made a vector string words2, and I tried to copy words1 into words2. Hi there, this doesn't matter. I get a seg fault, right? Because, well, there's no space actually here. This has a backing array of size 0. And so when I tried to copy things into it, the compiler complained, right? Or the runtime. And rightfully so. However, this is kind of weird. So here I'm copying words1 into words2, and I know beforehand the size of words1 when I made words2, right? So that actually worked. But maybe that's not always the case, right? Maybe when I copy thing from words1 to words2, I kind of want this to just add them to the vector as it normally would. And so there's a special function for that. It's called a back inserter. So you'll notice that instead of words2.begin here, I wrapped it in this back inserter function. And all this does is it calls, instead of using iterators explicitly on words2, it's going to call the words2.pushback on each of these elements. So this should work. Hi there. Oops. Yeah, sure. And so, yeah, when I built words1, it had 5 words, and so the capacity became 8. And now I'm basically doing the same thing to words2. I'm just adding them one at a time, and it's doubling every time that it runs out of space. And so here I also have a capacity of 8. All right. Questions? Okay, yeah, this is sort of yeah, it's not extra to the course, but it's not as heavily emphasized as the other parts of the course, right? So again, you should know, if you know how to write a for loop using iterators, that's pretty good prep for the final, right? And yeah, you know how to use pointer arithmetic, as we're going to see. So yeah, some of this will be useful. Some of it you may find dubious. So I'm going to here I'm going to insert I feel like I wrote that wrong. Words2.begin. Oh, right, sorry, I'm reading it backwards. Okay. So let's copy words 1 into words 2, and then here I'm going to insert at the beginning of words 1 all the words from words 2. Maybe it'll make more sense when we do it. So let's do it, and then we're going to print out words 1 again. Oops. Okay, so hi there. Okay, so words 1, the usual, and then I copied words 1 into words 2, so now I have an exact copy in words 2, and then I insert words 2 at the beginning of words 1, which means now I have basically this sequence of strings twice, right? So hi there, how are you? And then again, hi there, how are you? So that is this insert, which is, it's weird because I call it on words 1, and then I have to grab words 1's iterator to tell it where to begin. And then, well, I have to grab words 2 iterators, which kind of makes sense, but it is sort of a weird structure, right? I'm saying insert into words 1, where in words 1? Well, words 1 dot begin. And well, this being a vector, I can do pointer arithmetic. So I can say, well, don't insert at the beginning, walk forward 2, or like jump forward 2, and then start inserting there. All right, so printing out words 1 again, it says hi there, and then starting at location index 2, it copies words 2. So hi there, how are you? And then how are you? And well, I can also do, +1 here and -1 there, so that I copy everything but the first and last word. So now if this string has size 3 and I'm copying, oh, it's going to look, well, let's see if we can figure out what happened. Hi there, there. Right, so down here I said, well, skip the first one and skip the last one, essentially. So it only copied the middle one in, which was there, and it copied it into location 2. All right, so that is, and of course on top of that, you could do things like erase, which works the same. I could just say erase from this location in words 1 to this location in words 1, and then output it. So I'm going to, yeah, basically delete the 2 words in the middle. And then it says, hi there, you. So how are got deleted. All right, so that's basic. And this works, here we did it with vectors and pointer arithmetic. I mean, this will also work with lists, but of course you can't use pointer arithmetic. But any questions? All right. How am I doing for time? Well, let's try the same thing with a list or similar stuff. Also, we're going to sort with this list. Right? So here I have a bunch of students. These are students you're familiar with. We have a less than operator. So if I do call sort, it's going to by default use this less than operator, which says, oh, we're going to sort by alphabetical order by major. So, computer science comes before history and art comes before everything. So we're going to add a bunch of students to our list. We're going to copy our list to our output stream, and then we'll move from there. Yeah, something went wrong, huh? Oh, right. Actually, I left this in on purpose. I just forgot about it. So what went wrong? Or does any, I mean, let's take a look at our student class. So one thing we did not mention, this is a user-defined type now, right? So it's not a string. String has all of these operators overloaded, and so everything is just going to kind of work if you use a string. Not so with students. And in particular, what it says here is, well, it keeps looking for this operator, right? The stream insertion operator. And you can see here that I've commented it out, right? So if I don't actually overload a stream insertion operator, well, this behind the scenes is really doing the stream insertion operation, right? It's doing taking the first student, sending it to C out, and then the second student. So if I don't overload the stream insertion operator, I do not get to do this, even though it's kind of ugly, and why would you want to do it? But yeah, so let's put that back in. So now my student has a stream insertion operator, and now that copy command, copying to the output stream, will actually work. So there are all my students from my list. Well, let's call sort. So a linked list has its own sort function. This is not true of the vector. I can guess at the reasons because basically linked lists needs a special sort, right? In particular, because of the structure of it, there are efficient sorts and sorts that will not be very efficient. And so to make sure that you use the correct one, it comes with its own sort, right? In particular, we don't have random access. So I believe, I think this is merge sort, but that happens to work well. So now we're going to output our list of students again, but now in alphabetical order based on their major. Barely any change, right? CS is first. Oh, and then geography and math change places, and then physics is last. All right, so not too impressive, but I can sort it that way. If I wanted to, for instance, insert into my list, right? So let's say I have my student Bob, who's currently not in the list. I want to insert Bob, but I want to insert them in the third location. Well, this being a linked list iterator, I cannot do IT plus 2. I have to manually advance it. Again, this sort of follows what we know about linked lists, is that we cannot jump to 2 locations ahead. We have to walk there. And so there we go. Bob is inserted in the third location. What else? Well, this might be kind of tedious, right? I could set up a for loop and basically insert anywhere in my linked list. It's still going to take time proportional to how far we go, but I believe there is this IT. So rather than manually writing a loop and advancing it, I can just, I believe, hey, I got it right. Look at that. I could just use the advanced function, and that's going to run those 2 plus pluses for me, and then I can just insert using this advanced iterator wherever I like. Okay, no pointer arithmetic, right? So if I do something like this, plus 2, well, it doesn't. So for these iterators, it does not overload the plus operator. OStream, insert when you have access. Sorting uses the default. Oh yeah, one last thing. I can sort. So here we sorted by default using the less than operator. But let's say that I had this. So I have a function that returns Boolean and takes 2 students. In this case, these are const student references, but as long as they're student objects, and returns a Boolean. So here I'm going to say, well, any function that matches that signature will work, but in this case, I'm going to sort in increasing order of GPA. All right, so in my sort function, I'm going to say, well, this is in the student namespace. What is it called? Comp GPA. All right, so I can pass in this, this function. There's another function up there from my student class. Again, functions are just basically pointers to functions. So now when I sort the list, you can see that it's in increasing order of GPA. Stanley's first with a 5.6, and then Joe, and then Matilda, and then Amy. Okay, and then we insert Bob, and now Bob's out of order, but so yeah, I can pass in, well, in this case, it's from the student class. Here I have a global function. Again, it just needs that signature. Now these are not const, and in fact, I could pass these by value if I wanted to. Right? As long as I'm able to pass in two student objects and it returns a Boolean, this should work. So I can do, in this case, it's going to return, well, now we're going to do alphabetical order by name. So I'm just going to pass in that function. And there we go. So the sorted list, Amy, Joe, Matilda, Stanley, alphabetical order by name, and then we insert Bob. And Bob's a little out of place here, but I believe there is, if I'm not mistaken, there is a insert in sorted order function in the algorithms library, which, anyway, questions? Okay, 923. The deck, I'm going to skip. So we looked at vectors, and in particular, we looked a little bit at copying and inserting and erasing, but also a little bit about the capacity, right? The size of the backing array is important, especially when I'm copying to it. The linked list, we saw there's no random access. I have to walk to somewhere if I want to insert somebody somewhere other than the front or the back of the list. But I have functions that'll do that, the advanced function. It still takes, time linear in the size of the list or in the number of steps I'm taking to advance, but for convenience, it works. If I wanted to sort, I have to overload the less than operator. Well, I don't have to, but by default, that's what it's going to use. I can always pass in a function, right? Whether or not I have the less than operator overloaded for my class, I can just pass in whatever function I like. Decks are weird. I tried to look up the implementation. There's a very simple implementation that you'll take in 2402 if you haven't already. It's very nice. Apparently C++ doesn't use that. It does some weird stuff. But decks actually work pretty well. We saw that when I insert in the front of a vector, I have to move everything out of the way. Not so much with decks, right? So I get random access, but in some sense, I'm not speaking well today. I have some stuff in my deck that is, there's a, the start is here, and the end is, or just past the end is there. And so I sort of keep track of those two things, but I can insert at the beginning very easily and just move this pointer. And I can insert at the end very easily as well. And it sort of maintains that structure. And then, so in C++, it does some weird stuff. The nice thing about this is that I still keep random access, but I get really quick insertion in the front. If I insert in the middle, I still got to move things out of the way, but they work pretty well. We're not going to take them today. Let's look at associative containers. So these are, in some sense, well, you can think of it as a dictionary, or you can think of it as a hash table. Right. So in basically, containers use keys, and those keys are sometimes the data, or sometimes they're associated with data. So But the thing about associative containers is that they store them in C++ in sorted order, right? So if you don't want to take the time to sort your list, and then when you insert, make sure you're inserting in the correct location, you can just use one of these containers. So there's set, which is just the keys. Well, actually, I think we get into that over here. Yes. Set stores keys only, so your keys and data are the same thing, essentially. It does not allow duplicates. Or you can use a multiset, which again is keys only, but does allow duplicates. Or if I want to use key value pairs, then I'm going to use a map. So the default map does not allow duplicates, but the multi-map does. And then we have things like insert, find, lower bound, and upper bound. There are some interesting things you could do with this stuff. We're not going to take it too much here. We're just going to show you how to use multiset to basically store things in sorted order. There's a bunch of ways. All right, so again, we have our student class. You'll notice that, well, we're going to ignore this for now. We've overloaded this equals operator, and yeah, I've commented that out, but let's put that back in. We know we're storing in sorted order, and we know that if we don't implement that, then the sorted order is not going to work. All right, so I make a bunch of students, and then I'm going to make a multi-set of those students, and then I'm going to insert all of those students, and then use a for each loop to print them, right? So this is going to store them in alphabetical order by name, and so let's see. So there we go. We copy all of our students onto this or into this. Well, it's actually a tree. It's a binary search tree in the background. But it maintains the students in sorted order. All right, so every time I add a new student in, whether or not they are added in sorted order to begin with, they are placed in that order when I add them, right? So all that happens automatically, which that's a use case that we often like. Okay, so by default, we're using the less than operator, but let's set it up with some other ones. Now, this is a templated type. And in addition to this, I also need, there's an implicit second argument here. And this implicit second argument uses a default less than operator, right? But I can give it a second type, but now I need the type I need is a function, right? So that's what this is. This is a type that I can use to define a function. And in particular, this returns a Boolean, right? This means that it's a function pointer. And it takes two constant students as arguments, which is exactly what I need to sort, right? So, and then, so I said, this is my students. So I gave the type, and then I have to supply an instance of the type. And so if we look up here, we have this compare function that matches that function signature, returns a Boolean, takes two students, and now it's going to sort in increasing order of GPA. Okay, so we probably won't have time to take this semester, where we go into detail about all the ways that you can sort of define, you can make variables that store functions, and there's a bunch of different ways to do it. And one of the ways is to use this type declaration for your function variable. But here we're using it as part of, what did I do? Conflicting declaration, that's right. Only allowed one of those. All right, so we said increasing order of GPA, and you can see here they're stored in increasing order of GPA. Questions? All right, so the only drawback of using these is they are stored as const, right? If I take away the const here, like that's not just for show, anything that goes into my sorted well, a tree, I guess, but in this case, it's a multi-set, must be a const. And the reason being, if I'm allowed to change these things, then I could implicitly change the order, right? So if I store them in increasing order of GPA, and then somebody's GPA changes, well, suddenly they're not in sorted order anymore. So to mitigate that, the multi-set and basically all of these things that store things in sorted order, store them as const references. So you cannot change them. Once you add them, once you copy them into your multi-set, they cannot be changed. All right. So let's look at a couple other examples. This is kind of awkward, right? And, well, it's very awkward. Well, there's a simpler way to do that. I know I want to use this compare function, and I just use this, I don't know if it's a function or a macro, but it's a declare type. So it's going to take this, and it's going to figure out the type, and then here we add that it's a pointer to that type, right? So it's going to figure out what type of function this is. It's going to fill that in, and then everything else should work exactly the same. So it's a little bit of a shortcut. And they're still in increasing order of GPA. And then finally, so we talked about overloading operators. Yeah, let's get through it all today. So here's a class that's inside my student class. And I've overloaded the parentheses. And what does this let me do? Well, this lets me declare a class, an instance of a class called comp. And let's see, I wonder if I could do this. Is this public? Yes, it is. Okay. So I can make an instance of comp. Let's call it C. And then I can say, so what I'm doing here is I have, these are called, I believe, functors, at least in this context, or that might be the mathematical name. But C is just an instance of this class, but I can treat it as a function because it's overloaded this parentheses operator. And if we look, of course, it takes, the parentheses operator takes two student objects, so I pass it two student objects. It returns a Boolean, and so, yeah, not defined. I think I have to put this in the student namespace. There we go. So Bob comes before Amy. Does that seem right? Well, what did we do here? Oh, this is reverse alphabetical order. So yes, Bob does come before Amy in reverse alphabetical order. So yeah, that's essentially what this little class is. It's just a class that behaves as a function, and I believe in C++ they call them functors. And they're kind of useful. And in particular, in this case, for my multi-set, I could just pass that in. And then, well, I passed in this type. I don't even need to pass in an instance of the type now because the multi-set can make its own, right? So in this case, I'm going to store my students in reverse alphabetical order. And so yeah, Ted is first, and then Matilda, Joe, Bob, and Alice is last. So yeah, these are quite handy. Questions? All right. Finally, algorithms. This should, for your tutorial. Anything else I need there? No. So we're going to look at some of the algorithm stuff and just the basic structure of it, right? Because I believe I tried to force you to use the find. Now, when it comes to the tutorial, if you want to do it, you can write your own algorithms, right? I don't really mind as long as it passes the tests. In some cases, though, it does expect an iterator, right? So if you don't return an iterator, then it's not really going to work very well. So we've seen how we can sort lists, and we've seen a multiset which sorts itself. But how do I sort a vector? Well, a vector doesn't actually have a sort function. Instead, we use one of the sort functions from the algorithms library. So we're going to make a vector of students. We're going to push a bunch of students on there. We're going to use the output stream iterator. We're going to print out the students before sorting. And then we're going to sort, and then we're going to print them out again. And to start with, we'll just use the default sorting, which uses the less than operator. And in this instance, what does it do? It's alphabetical order. So let's go into okay, before sorting, we have Matilda, Joe, Stanley, and Amy. Once we sort, we get Amy, Joe, Matilda, and Stanley. Okay, so for the vector, again, you use the algorithms. Linked list has its own sort function. I believe this will also work on a linked list, but it's probably better to use the sort function for the linked list because it's specially designed. And again, the same as before, I can by default use the less than, but I can also use like, what do we got here? I have a static function called comp that returns a Boolean, takes 2 students as arguments, so I can use that. Where are we? Sort. And that, what does that do? Oh, yeah. Decreasing order by GPA. So yeah, Amy has the highest GPA and Matilda the second and Joe the third, etc. All right. All right, that's sorting. Let's look at some other stuff. So there are things which, if you've taken 3007, which a lot of you have not, but these are sort of these map operations. So I'm going to take this vector of students. I'm going to apply this all of function from the algorithms library. So from the beginning of the vector to the end of the vector, I'm going to see is everyone what? Now I need to pass in a function. This function needs to take one student as an argument and return a Boolean, right? So this is a predicate or a filter. So in this case, I want to return true for all students that are passing, right? So we're going to use this pass function. And now this returns true or false. So it's not really a mapping, but if all of, I think I need one more. And we'll say everyone is passing. And otherwise, if not everyone is passing, well, then the logical operator is that, or the logical negation of that is at least one student is failing. Okay. Let's see if that works. And what is passing is what? It's a friend. Where did we put it? I'm blind. What is going on here? Did I not write this? Well, let's just see what happens. It's there. At least one student is failing, and I believe it's Stanley. Stanley's got the worst. Where did I put that function? Did I put it over here maybe? I think I did. Yes, there it is. Okay. Passing in this case means GPA is at least 6. All right, so, well, we printed it out and we saw that Stanley is failing. Okay, well, we can actually do something about that. We're going to sort by increasing order of GPA. So let's try that again. Whoops. Okay, so now it's in increasing order of GPA. So like when the, people come around for inspection, we want to sort of sweep the failing students under the rug. So we're going to say, is everyone passing? And we'll say, oh, we'll just ignore Stanley at the end there. This is a vector, so I can do that sort of pointer arithmetic. And then when it asks, is everyone passing, it returns true because I skipped Stanley, right? So that's the all of. There is an any of, which is, logically very similar. Is anyone passing? Someone is passing. And in this case, the opposite would be everyone is failing. All right, so everyone is passing, someone is passing. Well, what if I just looked at Stanley? So from here, I'm going to skip 1, 2, 3 students. So now it should output everyone is failing because it really only looks at Stanley. So yeah, now it thinks that everyone is failing. There is the for each. So this is a lambda function. I don't really want to use that right now. But the for each function, what does it do? Well, the function itself is, I'm going to pass in a function to apply to every instance of a student that I find in this vector. And in this case, I just want to print the GPA of every student, right? So it doesn't have to return true or false in this case. I'm just going to apply this. And then, yeah, it should print all of my GPAs. So there we go. The for each. Now, again, kind of easy to write your own versions of these, right? So there's nothing particularly interesting going on. Let's look at the last couple examples. Sorry, I'm going very quickly on purpose so that we can get to exceptions next class. So I'm going to look for Joe. So this is find. It's going to return an iterator. I believe this is similar to what's on the tutorial. So I want to find in the vector something that equals Joe. So what is, I passed in a string here rather than a student. Well, again, it's just going to go to the default operator. So, well, the default operator for find is the double equals. So I can definitely find a student that equals this if I pass it in, but I also allow that, well, you can compare it to a string. All right, so we're going to pass in Joe, and Joe is going to be compared to every student using this operator, and it's going to return true if the name is the same as the string we passed in. So in this case, it's going to find a student named Joe, And if it finds it, well, it's going to return an iterator, and then I can dereference that iterator and print out Joe. So let's see if that works. And so did we find Joe? There it is. We searched using his name and operator overloading, and everything worked out great. So yeah, I believe I asked you to do something like this. Now again, if you come up with a hack and do it a different way, I don't mind. I do believe it expects an iterator in return here, though. I can make a second vector of students. I can do this copy if using the back inserter and a predicate. So I'm going to look at every student in StuVect, and if they pass, I'm going to copy them into StuVect2, and then I'm going to print StuVect2 to the standard output. To all passing students, Amy, Matilda, and Joe, and Stanley gets left off here. Okay, so the copy if Phil is kind of interesting. So I'm going to go from stuvec.begin to stuvec.end, and I'm going to say, well, fill it with Maddie. What does that mean? Well, again, I could give a particular student, but really all I'm using is this assignment operator. So when I say fill, I say, well, take every student you can find and make it equal to this. And what happens when I do that is, well, however I defined it, in this case, I simply change the student's name to whatever I passed in. Right, so this fill is going to change everybody to Maddie, and then I'm going to output the students again. So yeah, here's all my students, well, all the passing students, Amy, Matilda, and Joe. And then here are all my students, but renamed to Maddie. Okay, so there's lots of, and then, oh, here we find the min element as well. There's lots of interesting things you could do with these algorithms. Again, none of them are particularly difficult to write yourself, but you can sort of chain them together with operator overloading and do some cool stuff. Here I want to find the min element. Well, how does it determine what the min element is? Well, again, it's going to use some sorting operation. So I can, by default, use the less than if I don't pass something in, or I can use some sort of compare function that I designed myself. So it's not going to sort, but it's going to find the minimum element if things were sorted, and then print them out. Do I have a compare function? No. What do I have? Comp? Yeah. Or maybe not. Oh, I think I have static or whatever. All right, we'll just, by default, we'll just use the less than operator. So the minimum student is Maddie, of course. I think this, I don't know. Whatever the operator did. Anyway, you can find the minimum element that way. All right. So those are all the algorithms, questions, or at least the algorithms that you might be interested in. Again, none of them are too difficult, but you can sort of, using iterators, and you can do some kind of cool stuff. We've got 5 minutes left. I think we can get through this woo clap, and then next class we will talk about exceptions. And then that'll be it for the course, except for the review next Monday. No, it makes up for the missed. So if you do any 5 tutorials, get your full marks, or, you know, as long as you got perfect on all of them, you'll get your full marks. The 6th tutorial will be worth less. So I guess, right, because the other ones are worth 2%. I don't want to make it worth 2%. So it'll be worth a little bit less, which means that I'll probably take your smallest tutorial as the bonus, right? So the one you did the worst on, so that you get the highest mark overall. All right, let's see. We can get through all of these. What are the 3 main components of the standard template library? All right, let's do this one quickly. So please select your answer relatively quickly here, and we'll move on to something more interesting. This is just the warm-ups. And so we've been talking about, I mean, containers, well, vectors, lists, those are all containers. And we've been talking about algorithms in particular, just that last little bit, and iterators all the way through. So in this case, it is number 1. These are members of the containers, and these are, well, we have operators here, which is just trying to trip you up, right? So if you have not selected number 1, select it, or anything, and then let's move on. Sorry for, maybe I'll just go slow and whatever. If we end it early and pick it up next class, then we'll do that, just so nobody's scrambling. Which of these statements about iterators is true? Select all that apply. So yeah, they give you access to elements of a container. Well, that is the problem that it solved with the linked lists, right? We really had no general way to access those elements without iterators. So number 1 would be true. They allowed you to interact with a container in a consistent manner. Well, yeah, I can pass, right? We saw how copy took an output stream or a vector, right? So regardless of the container, we can use the same algorithm by using iterators as their arguments. They are an abstraction layer between containers and algorithms. Well, as it turns out, all of these things are true. So, but yeah, as long as you selected at least one, well, maybe we'll stop there for today. So next class, we'll complete the woo clap in the beginning, and then we'll go on to exceptions, and then that'll be it. So this is sort of a, yeah, all your hard work is done. There's light work now until the final. But yeah, do work on your assignment. I will, and keep an eye out for updates. Again, though, if there's a problem and you can solve it by using common sense, then I encourage you to do that, right? You don't have to, if it passes the tests, I mean, you will almost certainly get the mark unless you've done something egregiously wrong. So that's it for today. I'll see you guys in a couple days.